So chapter 8 is all chemical reactions, and most of you correctly identified what a chemical reaction is, but just for the record, we'll state it is the process by which one or more chemicals one or more substances are changed into one or more different substances. So there has to be a change in the actual substances that you're dealing with. The stuff that goes in is called the reactants, So we have, reactant A plus reactant B, and those are written on the left side of this here arrow. And what comes out of a chemical reaction are the products. So we get product, and just to keep life simple, we'll use product C and D. Can't spell. I mean, that's, most of you, I think, know that, I hope. So reactants in, products out. And here's the thing. Whatever the mass of this side is, has to equal the mass of that side. Why? What law of nature? Conservation of mass, yes. We cannot create or destroy mass in ordinary chemical reactions. Whatever atoms we start with, we end with. So if you're missing mass or if you've gained mass, it's a measurement issue. You didn't do alchemy here, which is good. Forgot to hit pause. So 4 basic indications of a chemical reaction: release of heat or light, production of a gas, formation of a precipitate. So you guys all know heat or light. You know production of a gas. Several you said bubbles. And you know color change. If something changes color, there's a good indication that a chemical reaction has occurred. The thing that is not quite as clear when people get to chemistry is this one, formation of a precipitate. How many of you think you know what a precipitate is? Okay, good. That's what I thought. That's the usual. If I have a solution, and you guys have been dealing with solutions a lot recently, as evidenced by our chaos in the lab, a solution is one substance that is evenly distributed in another. So you've been making alum solutions. When you have a solution that is just a saturated or unsaturated solution, it looks clear. There are no chunks. There are no crystals in it. Okay? At the point when that changes, what you see is you start to see chunks come out. Sometimes this shows up as, hey, the solution just got cloudy. It suddenly looks like milk. That's the formation of a precipitate. As long as it's clear, that's a solution. You can have a solution of multiple ionic compounds, and then when you put them together and it suddenly goes cloudy, that's what we think of as the formation of a precipitate. In some cases, that precipitate is so heavy that it will all settle out and you'll get a layer on the bottom. Okay, that doesn't always happen. Just a solution turning cloudy is indication of a reaction because that is formation of a precipitate. Okay, so now we're going to talk a little bit about chemical equations. You have some background on this. It is how we describe a chemical reaction, and it is the centerpiece and the cornerstone of everything we're going to do for the rest of the year, basically. You have to be able to write a chemical equation about anything we describe. So it describes it using symbols and numbers because we're using the chemical symbols for the compounds that are reacting, and we're using numbers to represent relative amounts. So you represent symbols, formulas, identities, states, relative amounts. The equation here, so if I had covered this up, which I meant to, whoops, you, because you know how to read formulas and name them, could say that that is ammonium dichromate, right? You might have to take a few seconds with your ion Bible, but you'd figure it out. And it is reacting, and it's forming N2, which is just nitrogen. It's forming Cr2O3, which is chromium 3 oxide, and it's forming H2O, which is water. That part you probably already can get from physical science. The part that I think is new for most people coming into chemistry is the little subscripts. So let me enlarge that, and we'll look at those a little more closely. If you notice these little abbreviations in parentheses behind each chemical, that tells you the state of matter that it's in. So we have a solid which is decomposing to form two gases and another solid. It's basically giving off the other solid. We don't always have state information in a reaction, and if you don't have it, don't guess. You know, you can't do that. But when you have it, you should always specify it. This is critical for everything that we're going to do from here on out. When you have a chemical equation, it has to represent known facts. Just because you say two things react doesn't mean they will. Not everything reacts. Stick a chunk of copper in water. Does it react? No. Stick a chunk of sodium in water. Does it react? Yes. Robustly, vigorously, with sparks and, you know, little puts as it off-puts hydrogen gas. It has to represent known facts. You can't, I mean, you can write that copper and water react to form copper hydroxide and hydrogen gas, but it doesn't make it true. It doesn't happen. So you have to make sure that it represents known facts. You have to have correct formulas, which is mostly the skills you learned in Chapter 7, and a few new ones that you're going to master here. And you have to satisfy conservation of mass. That's the balancing part. That's pretty easy. By the end of this chapter, here are the things that you're going to be able to do. You're going to be able to identify and describe a reaction correctly. That means writing an equation for it from a description of an event happening. So going from a description in the real world to a balanced chemical equation. You're also going to be able to predict the products of reactions and whether or not a reaction will occur. It's not a whole lot. There's a lot of stuff packed into it. Okay, when we talk about representing known facts, very often, here's what happens. Very often, you know the reactants, you know the things that are going in, but you're not sure about the products. And so how do you identify products? You can run chemical analysis. If you have access to a lab with that kind of equipment, we don't. So in general, we rely on reliable sources. The internet sometimes is, sometimes isn't. The chemical forum that most of you joined is a good source. But your textbook's also a great source, and that's a good first source. So, you know, those are reliable sources. I try to be a very reliable source. I have screwed up, but I try never to make the same mistake twice. So, and that's the big thing on known facts. The one last thing I want to talk about before we disembark for our long weekend is, so you know about having correct formulas for ammonium nitrate or iron 3 oxide. The piece that you haven't encountered yet, or if you did, it might be pretty dim, is that for pure elements, they aren't just H or N or O. There are 7 that are always diatomic in nature, and if you get your periodic table out, you can circle them. So the ones that are always diatomic when they're on their own: nitrogen, oxygen, hydrogen, fluorine, chlorine, bromine, and iodine. Those 7. And of course, most often we actually look at hydrogen being over there, so we'll do that. But you can come up with some sort of mnemonic for those, remember them. Some people call them the heavenly 7. Most of those are gases we find in the atmosphere. But there are 7 of them, and they're always diatomic when they appear by themselves. So if you see that a reaction produces hydrogen gas, and you write that as just H, your balancing is going to be off. Hydrogen gas, when it's produced, is H2. If something produces nitrogen gas, again, it's not just N, it's N2. Same for oxygen gas. And all the halogens in their elemental form come as diatomics. So the other ones, and these are stranger. Well, the metals are easy. So iron, carbon, any metal in its natural state is by itself. And the way I remember this is scary metal guy walks alone. And I have this image in my head of a guy with like a leather jacket with spikes and, you know, Liberty spikes and all kinds of facial piercings. And he's a scary metal guy. He walks alone. That's what I got. So the metals always are by themselves. Those are relatively easy. Heavenly Seven, diatomics, metals, walk in solo. The ones that are really weird and you will mess up and I will mess up are sulfur and phosphorus. Sulfur exists as S8. Don't ask me why. I'm not a particle physicist. Sulfur exists as S8 and phosphorus exists as P4. It's handy that the weirdos live side by side. And we don't run into a whole lot of situations where we have elemental phosphorus or elemental sulfur, but when they come up, that's something to remember. We'll stop there, and I'm not going to give you any homework or practice or anything over the long weekend. Go take a break. When we come back on Monday, we're going to go full speed into starting to balance equations. That's it.